for us, that's in the lecture. Yeah, I think that any of you, if you wanted to have the recording, yeah, I can send you the link for the recording, especially so if you are operating the software. Okay, so let me share my computer screen. Yeah, okay, so let's start into, yeah, so making my screen. Yeah, okay, so I think so now everything is set up. Yeah, so can you see my computer screen, Futiao?
Yeah, very clear.
Great, yeah, thanks. Okay, so today I will talking about how to build in the deep tunneling inducing the rock burst. Yeah, I think the rock burst should be a topic which is quite interesting, especially yeah, so for your group. Yeah, I think that's yeah, so the group yeah, Daniel is one of the group working out. One of that's the most important group working on the rock busting. I think now in your group is not only using the computations method to building the rock bust, you are also using the macroseismicity of the monitoring try to early warn of the rock bust. Yeah, okay, so I talking a little bit about that in the task, which is yes, a Mark asked me to do. It's working on the dam. Yeah, so the dam. Yeah, so what I do that in the first step. So I calculated the in situ of the stress. So this is only applied as self-weighting only. Yeah, so later after that in the presentation, yeah, I will talking. I'll ask a few of that in the questions yeah, for Marka and Duan I don't know if Duan is here. So today, yeah, okay. Anyway, we leave in that installation. You can see, yeah. So yeah, I noticed that from Duan it said we have the RFPA code. Yeah, when did be able to deal with the problem with this scale. Yeah, you can see that for the HFDEM, there is no problem for deal with the problem at this scale. So we can get in that in the mass of the initial of the stress distribution due to that in the self weight. Yeah, we can compare that in the ways that yeah, if we consider here, yeah, we can simply to using the a vertical stress equal to rho GH to calculate it. We can check and on that. Yeah, but obviously, so for this problem, due to we have this the dan here, and the dan have the differently the self weight, and we have this the river valley here. Yeah, you can see here, obviously have the stress concentration. So if I zoom up to that the region, so you can see clear of that this stress concentrations there. Okay, so that one, I will leave that at the end of my presentation, yeah, for us to have a discussion about that, how we voting this problem. Okay, so what I want to talk today is about the rock burst. Yeah, actually is based on one of my PhD students' paper. Yeah, I think that I show you these papers before. Okay, so let me show you that's in the paper again. Yeah, so the paper is like, yeah, so this, yeah, so which is written by Dr. Han. Yeah, so he is now an associate professor in a Chinese university. Yeah, he just graduated in last year. Yeah, so what we using that problem, so you can see here, this is actually is a problem in China, in Jinping. I think that's many of you from Dalian University of Technology has working on that in the Jinping of the rock burst that before, either that's using the numeric method or using the macroseismicity of that monitor. Yeah, okay, yeah, so yeah, obviously, so this paper, so that's quite comprehensive. We won't have enough time to introduce everything. We will only introduce that in the simplest of the case for a circular of the tunnel and in the massive of the rock masses. So we wanted to consider that in the geometry here. Okay, so let me make my screen. Yeah, full screen so again. Okay, so we will only consider that as one of that the simplest of the problem. So we consider that's the tunnel. So as we know for Jinping, so we have that situated in Sichuan province. So which is this tunnel, which is the average of the bearing of the depth, which is more than 2,000 meters below of the ground. And there have that the very high of the in situ stress. Okay, according to we use that published paper from that in the Wuhan Institute of Rock and the Soil Mechanics. Okay, for that paper, yeah, I think that's paper is that say we have that in the vertical of the in situ stress, which is 60 megapascal, and the horizontal, which is 45 of that in the megapascal. Okay, so when you have that initial stress in there, when you dig in a tunnel, obviously which will introduce the stress concentration, and this stress concentration which will introduce that in the failure. Okay, so here, yeah, I taken that a few of that in the steps from the numerical modeling, so you can see how that in the failure processes look like. Like if we without of the joints, or if we have that adjacent of the functions there, yeah, obviously, so that's the adjacent of the faults have an important influence on that the rock of the busting. And therefore, that's the faults, or that's called the joints, depends on that's the parameters of the joints. You will have that influence as well. So here, that's demonstrating if we have that the deepening angle of the joints, which is different. So you will have that in the rock boson of the behavior, which is different. So you can see if we have that in the joints which is deepened towards of the tunnel, so then in that case, which we're introducing a bigger of that in the damage zone. Actually, so this is that in the case which is close to the actual of the situation. So if we have that in the joints, which is deepening away from the tunnel, so you can see that's in the excavation introducing the damage, which is becomes smaller. Yeah, if you have that joint which is close to the tunnel, which will influence, which is causing a bigger of the excavations damage zone as well. Okay, so here this is that's a video which shows the from the numeric simulation. So you can clearly see. So after that excavation, how that's the damage which is occur around the tunnel. And then after that, you will have that in the block, which is fell off from the tunnel. So that's what we usually, which is called that in the rock boat. Since for our case, we have that in the vertical of the stress, which is bigger than that in the horizontal stress. You can see we have that in the stress concentration, which is mainly around that in the two sides of the tunnel. So then you have the majority of that failure, which is around that in the two sides. For the case, suppose if we have that massive of the rock masses. Yeah, but for that the Jinping of the tunnel, according to that the field investigation, so you have an adjacent of the faults or could the joint there, then in that case, the majority of that the fall of the rock block is actually which is from the uprighting of that in the corner. Yeah, okay, so we in that paper, yeah, so this one we weren't really talking that today. Yeah, for that paper, which is considered that's the effect of the faults of that in the location, and the different location which will influence to the rock boson of that's in the behavior. Yeah, obviously from for the numerical simulations results, we can base on the numerical simulations results to do some of the parametric analysis, do some of the quantitative analysis, like in that, and we mapping to see. So what is that the excavations of that the depth? Yeah, so this is what this figure is showing. And if we have that in the force, we have that in the deepen of the angle, which is different. So that will influence that one as well. And for the what we simulated that in the GP's case, we have that in the vertical stress, which is bigger than the horizontal stress. Yeah, you can do a series of parametric analysis. So you define an oscillations ratio. So oscillations ratio, we use that in the horizontal stress divided by the vertical stress. So then you get that in the lateral oscillations coefficient, which is K. Okay, if you adjust that in the K, then that will be different. Okay, you have that in K equal to 0.1. Since we have that K, that's the horizontal stress divided by the vertical stress. So then that means you have the vertical stress, which is much bigger than the horizontal stress. So that explains why. So you have this is that on that's the two sides. So when you have that K, that's equal to 0.9. Yeah, so then in that case, you have that the horizontal stress bigger than the vertical of the stress. Okay, anyway, so here, this is that, yeah, for the setting of that in the border, you slightly to change that in the input parameter. So you can do a series of the parametric analysis. Yeah, for the case, you can, if you change that in the tunnel shape, from that in the circular to that in the square of the tunnel, or that's in the host shore of that in the tunnel. So you can see when you this the tunnel shape has an important influence as well. Yeah, the worst the case. So if we using that in the square of the tunnel, then in that case you were introducing bigger of that in the excavations that is damaged them. And for the host shore of that tunnel, yeah, at the bottom, so there, which we're introducing the significance of the stress concentration as well. Then there's the stress concentration, which is causing a measure of the stress introduced in that in the failure. So we know that for the deep tunnel, yeah, so you have that in the stress introduced in the failure, so which is important. If we have that in shallow tunnel, so that's the structure controlled failure, so that's more important. Okay, so this is the problem which we stated into there. Okay, how we can model this problem and how specifically how we using that in the our software. So that's the HFDEM to model this problem. Okay, so this is that in the task today. Okay, to model that, so again, I will introduce that we using the a HPC version, yeah, instead of that using the GUR version. And for the modeling, which will still follow this step, so this is that, yeah, I have that introducing that many of the times. Okay, then I will not go through that. Okay, so for this problem, which is different from the problem which I introduced before, is that unlike for the previously, initially, so we have that in the sample actually is this stress-free. Okay, no matter what we introduce in that in the uniaxial complex test or the resilience test, or that's in the dynamic UCS and BTS. So all of that's in the case before we add in the load. So we know that's in the completely stress-free. But for this case, we model that in on case. That's in the okay. So suppose if we have that in the stress-free in a rock. So if you excavate in autonomous there, you won't cause that in the rock of the rock burst. Okay, so the important things here, that's you need to represent that in the in situ stress, or we call that in the geostatic stress. If we use the ABCOS, so that's called that in the geostatic stress in your analysis. Okay, so What we consider here is that, yeah, we consider rock masses. Okay, so this rock mass is what we consider here, actually, which is 30 meters multiple 30 meters, okay, which is a big scale of the problem compared with the previous, what we introduced that over that's the laboratory scale. So what we consider that's in sample, which is that's a few of the millimeters. So like that's the typical of the UCS test. So we have the diameter, which is 54 millimeters. Then we have the height. So that's 2.5 multiple 54. But for this case, we consider practical of the engineer problem. So we burden that which is 30 meters multiple, that's in 30 meters. Okay, the first step we needed to represent that in the in situ of the stress. So as we said, we have that in the vertical stress. So for our case, we have this 60 megapascal and a horizontal stress, which is 40 of the megapascal. So what we do, we divided that into two stages. Okay, so I have that's the first stage, I call it that's the step one. So I calculated the geostatic of the stress. Then the second step, which is I do that's the failure of our analysis. Okay, so here, yeah, so for our software to calculate the geostatic stress, so actually we have a few of the ways to calculate that. Okay, the simplest way is that we use we do not do any of that in the changing. We just using that in the normal of that in the way. Yeah, as we know, we using that in the HFDEM, we have this that an explicit integration. So if explicit integration, so which is suitable to burden the stacked problem. But actually for here, we have that in the initial stress, actually you have that in a static problem. Okay, for you to using the dynamic method to burden the static problem, as what we introduced in previous for the static unit X complex test or the Brazilian's test. Yeah, for that cases, we needed to use the which is called that's the dynamic of that's the relaxation to consider that a static problem. Then in that case, you need to use that and so-called the critical of that's the damping. Okay, critical damping, actually, so that one, which is quite slow, we were introducing here using a new of that method, or we say not that's new. So that's implemented into many of that in the software as well. So like that in the famous of the software in the geotechnical engineer, we know that's in the ETOX software. So that's the flag. So they have that in the implementation of that one as well. Okay, so for me to introduce that in the initial of the stress, let me introduce a simple of the problem. Okay, firstly, let's ignore that's the overburden stress. So we making that equal to 0. Okay, then in that case, for you to consider on a rock masses, so then you will only have that in the safe weight. Okay, we ignore that's the horizontal stress or that's the vertical stress. We consider that's from the ground surface. Yeah, obviously for this one, so you will only be able to burden that in a shallow of depth, like in what I have here, this is 100 meters. Okay, if that's we using this method, for example, to burden that in the GPGPU of the case, so you have that from the ground surface to deeper underground, which is 2 kilometers, which is 2.5 kilometers. So then in that case, so you need to build in a huge of that in the border. Okay, so that one we will introduce that later. Okay, at this moment, we just consider that in a rock mass which is from the ground surface to that in the deeper underground. Okay, we consider that 100 meters. And here, we do not have that in the geologic of the stress, or we so-called that's in the tectonic of that in the stress. What we have that in, we only consider that in the safe weight. Okay, so for this one, we can easily to using that the formula, which is low GH, we can calculate that in the vertical of the stress. Okay, the purpose of why I introduced that, I wanted to you, I wanted firstly to do the calibration. Yeah, for also to do the numeric simulation. For the simple of the problem, we should have this is consistent with that's the analytical solution. Otherwise, yeah, nobody know. Yeah, so you are right and you're wrong, or even for yourself. So you do not have the confidence in that as well. Okay, for my case, I firstly to build in that the simple of the problem, which can be solving that using the analytic method as well. If I have gotten that, which is consistent with each other, so then later, when I apply this to the more complicated of the problem, so then in that case, you have that in the analytic method would be able to solve that. Yeah, so yeah, I'm confident since I did that in calibration against the simple of that in the case. Okay, so what we consider here, we have that in the input of that in the parameter, which is like this. Okay, so here till this moment, we have introduced a few of the examples. So you should aware what is that in the input parameter. Okay, so let's go through that in the input parameter. Okay, we consider that in the rock of the mass, we have a density. Okay, then we consider that in the elastic modulus and that's in the Poisson's ratio. Then after that, we using the Bernoulli infinite criteria. So then in that case, you will have that in the tension strength, the cohesion, and the friction angle. Yeah, so we consider that's in the strength softening. So then we have two parameters which control that's in the failure. So one of that, which is the bullet one fractal energy, then that's the bullet two of the fractal energy. Then the order of the parameter, we have that's the numerical of the parameter. Okay, so the numerical parameter, which is here. Okay, so we have that in the contact of the penalty. Okay, we say the contact penalty, we usually use this 10 times of the elastic modulus. You can see we have the elastic modulus, so which is 12.2 gigapascal. So then we have that contact penalty. So we using that 10 times of that in the E. So that's why that's hit there. Then for the cohesive element which we insert in there, okay, before that's fail, so we have that in the cohesive element should not affect the continuous behavior. Then in that case, for the penalty of that in the cohesive element, what are we using that? We using 100 times of that in the E. So that's why we chosen that in here. Okay, so this is that in what we introduced that in the before in the previous of the presentations. So, okay, besides that, we have that in an average of that's the animal size. So average animal size, we need to use this one to calculate the critical damping of the coefficient. So as I introduced before, if you look at that in our previous of the presentation, so I say we have this in the this one, which is on a parameter, so which is related to the average of the strength, so which were related to that's the density, so related to that's the elastic modulus. So this is that's a function. Okay, so the previously of the presentation, I introduced this parameter, so that's detail. Okay, so this is like the case. So suppose if we use in this case to do that in the to get in that in the geostatic stress, or that's in the initial of the stress caused by the self-weighting only. Okay, so we can get in that in the stress distribution. We know at the surface here, so we should have that in the vertical stress equal to 0. Then at the bottom, so we should have that in using low G multiplied H. Yeah, so then here, this is that's the numeric simulation results. Then compared with the analytical of that solution. So you can see either that's in the horizontal or the vertical. So you have that in the exactly the same as the analytical. Okay, so what are we using here? That's the critical damping. And for this way is not so efficient. Okay, so then we implemented that in another of that in the method, which is called the look damping. And this why we needed to introduce the look damping. So the look damping is that you look at that in this figure. So for the critical damping, we needed to calculate in that. Yeah, so about 0.5 million of the staples, so then we are achieving that in the static equilibrium. But for we using the look damping, we only needed to calculate a few of the staples. So then you will be able to get that in the static equilibrium. Okay, so here that's introducing that in the, or we know for our HFDEM software. So what we solving that, we solving this equation. Yeah, so this is actually, so that's Newton's second law. We're using the explicit time integration. And here, this is that a dynamic problem so anyway. So you need to use that in the critical damping. Okay, this critical damping, that's the eta of that in the parameter, actually, which is implemented that into our constitutive equation. Okay, so besides that one, we say in order to speeding up the geostatic of the stress calculation, we introduce a look damping. Okay, this look damping actually which is controlled by a parameter which is called the alpha. And for the critical damping, which is controlled by the parameter of that the eta. Okay, so for the look damping, so that's work case which is considered the unbalance of the force. And then to put in on a coefficient to multiple the unbalance of force to quickly make that becomes that the balance. So that's the principle to apply that in the look of the damping. Okay, so this is that I say I have this method which is calibrated against the simples of that problem, against that's the analytic of the method. So now I will apply this into that more complicated of the problem. Okay, I will apply this and that into the problem which we are starting here. Yeah, so first to model this problem, so what we do is that initially, okay, we build in that in the geometry. Okay, so you can build in that geometry using any of that in software. So what I do that I will according to what I have been doing. So I will using that in the abacus to build in this of geometric model. So actually it's not necessary you must use in the abacus. So for my PhD student, so that's PhD student. So actually, so what he uses that is using ANSYS to building that the geometry of that in software. Okay, no matter of that in what kind of software what you build in that. So what we needed to use in that, which is the mesh connectivity of that in the data file. Okay, so for that one, let me with exiting that in the my PowerPoint presentation. Okay, so let me show that in the input file. Yeah, obviously before this and that in the presentation, I already prepared that in the input file. Okay, so similar to all of that in the previous of the presentation, I will share this input file is to you after that in the presentation. All of that in the previous the input file. So all of that's now available. That's in the computer. Okay, so this is that in the file which I prepared that. Okay, so this is that in the input file. Okay, so this is structure of that in the input file, which is exactly the same. Okay, in this case, we only have one of that in the rock of the part. Okay, so then we have that in element and that's in the load. Okay, so I have already put in that into the abacus. Let me show you. Okay, so firstly, let me get rid of this one. Okay, what I do, I just import in that in the file. Okay, that's in the import that's in the model. Okay, so this is that's in the rockburst of that's in the input file. Okay, which is like this. So you can see, so what we are interested is that in all rounded that's in tunnel. Yeah, so for my PhD student, he do that a little bit conservative. So actually for the cases is unnecessary. We need to use the uniform of that in the basis everywhere. So we can only needed to use the density of the basis all around that's in the tunnel. Okay, let's zoom that's in the part all around the tunnel. Yeah, so I have that in the tunnel here. Inside of that in tunnel, I mentioned that using the element in that in there as well. Yeah, actually, so my PhD students, so he mentioned that inside of the tunnel, which is using the density of the base. This is not absolutely necessary, since we know that in nature we have this part, so we will have this part which will be excavated anyway. Yeah, so when you have that, the part needs to excavate it. So even you using that, the density of that measures won't improve the accuracy of this. Okay, so in this, I define that a few of that in the sets as well. That's for later for me to apply the boundary condition. Okay, let me show you that a few of that in the sets. Okay, you can see which are defined as that sets. Okay, so what is that in the set? Which are defined as that in here. Okay, let me highlight this one. So I define actually you define that in the boundary. So I have that in the bottom boundary. Yeah, so here I define one of the points. So the one point in the center of that in the bottom of the boundary. So here I will apply the different boundary conditions. So that's the later. Okay, then after that I define that in four corner as well. Okay, then I define the left boundary, the right boundary. Then that's in the top of the boundary. Okay, so this is that what I implemented that using Abacus or using any of that in the order of the software. Okay, so then after that, let's come back into that in the component presentation. Okay, let me swap my screen. Okay, we build in that in the border. So if we have that in a close of the view of that in the bottom or around that in the tunnel, so which looks like you see. So this is the part which we need to focus on. Okay, so what we do is that we needed to apply an initial of the stress. Then we divided that into two steps. Okay, so the first step, what I do is that I needed to apply the initial of the stress. And then the second step, I needed to do the failure analysis. Okay, then here, which will have a part. Yeah, I think that this is that the running control of that the input file. As I said that before, of course, we needed to use that in the HFDEM software. So you need to have two files. One of that file, which is the mesh connectivity, then the other one, which is the running control file. The running control file, which is control of how that's in the running. Okay, so here that's particularly, yeah, which is talking about that in this section. Yeah, so for this section, for all of my previous presentation, I just skipped this one since this is not related to the previous presentation. Okay, so for this time, I was specifically to talking about this. Okay, this is that which is control how we apply that in the geostatic stress or apply that in situ of the stress. Okay, so let's go through this. Yeah, in the previously the model, I always ask you to say that's zero. So zero means that you have that in the model, which is initially that's stress free. Okay, so if that's zero, then in that case you can ignore all of that in the parameter, which is here. Okay, for our case, so we need to have the initial stress. So that's I put in that in equal to 1. okay, equal to 1, that means you have that model. You need to consider that's the initial stress. Okay, for the initial stress, we consider that's divided into 3 of the cases. Okay, so the first case is that if we have that 0, means that this one is that the step 1. So we want to use this, which is to generate of that the in situ of the stress. Okay, if you have that equal to 0, so that means we calculate have that's the step 2 of the calculation. So that's we already completed that's the initial of the stress concentration. Okay, if we have that given this parameter which is equal to 2, that means okay, we do not divide it that we ask the software automatically firstly to calculate that the initial stress. So then after that, the initial stress, which is to do that the directly to do this step 2 of that in the calculation. Okay, so what I do here, I wanted to separate that. So firstly, yes, so demonstrate how to calculate the initial of the stress. Then I demonstrate how to calculate that in the both that in the failure analysis. Okay, for the initial stress, we have 3 kinds of the method to calculate the initial of the stress. Okay, the first one is that as the example which I just introduced, suppose if we have the problem which is quite close to the ground surface, then in that case, we only need to consider the self weight. Okay, if you put in that equal to 0, so that's only consider self weight. And then the other one is that I needed to give a stress tension. Yeah, so like this one. Okay, I have that in a rectangle for the rock specimen. Yeah, so besides you have that in the vertical stress and the horizontal stress, if you have that in the shear stress, need to apply to this one as well. Okay, so then in that case, we say that's in the tension of the gradient. And what is that in the gradient? Okay, so we know that's in a we consider our rock masses, so you have that in the self weight there as well. Okay, you have here, okay, suppose we have this the y direction, and we have this is that's the minimum, and this one, so that's the maximum. Okay, suppose if we have this depth, which is not quite big, so then I have that in the stress at the y minimum and y maximum, that's do not have big difference. But suppose if you consider this is hundreds of meters, then in that case, you have that in the rock mass, you will have the self weight. Then in that case, so you will have that in the vertical stress at the top and the bottom, which will be different, since at least which were different by the self weight of the rock masses there. Okay, then if you need to consider that one, okay, then you using that in which I have that in which is Latin green of Latin color. Okay, for our case, what we need to consider here, okay, we using that in the third of that option. Third of the option, we given that in parameter which is equal to 2. So that means since we have that label which is starting from 0, so third of the option actually which means 2. Okay, so then that we will apply that in the situ of the stress using this one. Okay, you can see here, we have that 3 of the direction, x direction, y direction, z direction. Okay, for 2 dimension, you do not need the z direction. Okay, we put in that in 0. Okay, for the x direction and the y direction, x direction, I apply an overburden, which is of 45 megapascal, and the vertical direction, yeah, I apply that in 60 of that megapascal. Okay, so for me to visualize this, let me using that in a figure to represent that. Okay, so this is what is represented in that one. If I draw a figure for that parameter, okay, I consider a rock mass is here. Yeah, so I consider that's the minimum and the maximum. Actually, so what I consider that's 0. So this is 30. Okay, I consider that's 30, but 30. Yeah, so that's why in the parameter which is here, so you have that in the minus 30. Oh, sorry, actually I have this that which is 60 meters. So multiple 60 of that meters. So I have that in the central, the origin, which is in the middle of that sample. Then here, that's left side, which is minus 30, then right side, which is a positive 30. And then here in the vertical direction, below that is minus 30. Then above that is a positive of that 30. Okay, so that's what I apply here. So in the vertical direction, so I apply that the surcharge or apply the initial stress here, or apply that 60 of the megapascal. And in the horizontal direction, so what I apply, that's the lateral stress here. So that's 45 of that the megapascal. Okay, to tell that in the software where I apply that, I needed to give that in the X and Y direction. What is the minimum of the coordinate, and what is the maximum of the coordinate? Okay, since I have this 60, multiple 60, and I put in the origin at the center, so then I have that the maximum is 30, otherwise minimum is minus that's 30. Okay, for the boundary condition, what is the boundary condition for the first step of the initial of the stress calculation? So I using this boundary condition. So I put in that in the center of that in the point. Yeah, so that's why in the opticals I define that in the bottom of the boundary. So center, I fix this one. So that means the X direction and Y direction. I do not allow that in the movement. For all of the other point at the bottom boundary, I put in that as the lower boundary. So that are a free move to around the horizontal direction. But when you allow you move that in the vertical direction. Okay, then in this way, so then I will be able to build in that in the in situ of the stress. Yeah, obviously for our software, this is not the only way. So we can have that in the order of that in the boundary conditions as well. Is that for the center of the problem? You can use in the order of the boundary condition. You can use in this kind of the boundary condition. Okay, you using that in the fix the left of the point, and then for the order of that in the bottom boundary, or that's in the left boundary, you using that in the lower of the boundary. Okay, for the bottom boundary, you do not allow the vertical movement. That's why you apply on your solve charge into there. Then the stress can build up there. Otherwise, if you do not fix this boundary, so you will have this stress which will be released. And here, this boundary, you need to fix that in the horizontal direction. Otherwise, you will have this stress is released. Okay, no matter which of that in the boundary, so you use that, then you will be able to get in that in the in situ of the stress. Okay, so here, as I said, we have another type of that in the way to apply that in the in situ stress. Okay, so I have that in the firstly, I have that in the calibration of the example. I use this type of that in the boundary. Yeah. So what I apply that in, I apply an in situ of the stress. Okay, so for this one, you can apply that in situ stress, or you apply that in equal to 0, like that in the calibration. Okay, so for this one, yeah, what I in this in this slide what is demonstrated, you have that here. Okay, so here I need to, yes, so stress into that. If you use that in the stress and tension, you need to give that in the sign here as well. Okay, so we have this that in the compression. We have that in the sign of the convention is that if you have that compression, you give that negative. So if you have that in the tension, then you get in that in the positive. Okay, here we put in that in the stress, which is 50 of that in the mega of the Pascal. Okay, here we given that in the stress and tension. here is different from that in the pressure. You can see for the pressure, what we given that in for the previous one, we given that in 60, but actually we put in that in a positive value there. So that's because that's in the pressure. Pressure actually, so you do not have that in the sign of that in the there. Okay, so the purpose which I wanted to introduce in that, yeah, since for the previous of the cases, for us to apply the initial stress, so you were getting the initial stress, which is everywhere that will be the same. But for some of the problem, maybe the self-weight is important. So you have that, okay, suppose we have that stress in here, that's the y direction stress in y1. And then here, this is that in the stress in y2. Okay, for the previous of the, what I used in the pressure and the traction, I was getting exactly sigma y1, which will equal to sigma y2. But we know here, if I have that in the rock mass, which is significant depth, we have the self-weight. This self-weight, so if we consider that in self-weight, you will have that in the stress added that in the y2 should be equal to the stress added the y1 at that's the low GH. Okay, for that one, so we can consider this one as well. Okay, so then you can, given that the initial stress, so then you specify the gradient. Okay, the gradient. So whether you have needed to using that in the gradient. Okay, then you given that in what is the stress in the gradient direction. Okay, for our case, we always, so we have that self-weight, which is applied to that in the vertical direction. Yeah, but for some of the experimental, laboratory experimental, is not necessary, you always have that in the y direction. Okay, then you given that in the stress gradient. Okay, so we say the stress gradient at the top of that. So I have that self-weight introduced, and that's 0 upon 0. Okay, so then you given that in, yeah, of that in the gradient. Okay, so for this one, we wanted to use that one. We simply consider that, and since what we consider here, this is that 60 meters. We have that depth actually, which is 2.5 kilometers. So you have that 60 meters of self-weight, which can be ignored. Okay, we do not consider that as a gradient. So that's why we using that in the sort of that option. Okay, so let me clean my computing screen. Okay, so that's the first step. We using this kind of a boundary condition. Then the second step, we needed to change that in the boundary conditions. We using this kind of boundary conditions. We all of that in the outer side of the boundary, we fix it. Then for the corner, we fix that in the other way. Okay, so this is one kind of the boundary condition. Yeah, you can also use this kind of a boundary condition. But when you're using this kind of boundary condition, so you need to keep that in the overburning of the stresses there. Otherwise, you will have that in the stress release it. And for this one, yeah, you can remove that in the one. Since for this one, we fix in the boundary, so you making sure so that in the initial stress wouldn't be released. Okay, so this is that in the step one. After the step one, you calculated that. So you can see you were getting everywhere. So that's the uniform. Yeah, although you notice that and have that in the variation, but you look at that in the values here. So I have that in the scale here. This is 60 megapascal. Here, this is 60 megapascal. Yeah, I can consider that's a vertical stress. And here, this is that in the horizontal stress. Okay, if you use that, consider a scale, you can see here, everywhere also you getting that uniform. That means you getting the uniform of that in the stress here. Okay, so this is that in the step one of the calculation. Okay, so I have already prepared that in the input file. So I show you that in the input file. I will give you that in the input file of this presentation. This is the step one. Okay, step one, what we needed to use in that. Okay, we have that in here. Okay, so for this one, when you run, you just need to copy this one. Okay, copying this to that's the exe file. Okay, to the exe file, I have that. Okay, so I copy this. Then I run that. Okay, I run that. I will get that the initial stress. Okay, I will not demonstrate in here. Actually, so this is even you run that, it's only taking a short time. Yeah, so when you run that, but then you go to toilet, then you come back, and then this will be able to finish. Okay, I already calculated that in here. Okay, I show you that in. Yeah, in the visualization, okay, I show you that in the calculating the result. Okay, this is that in the step 1. Okay, so rockbursts, so that's in the step 1. Yeah, so we can consider 2 of the cases. You can consider, yeah, if we do not consider the self weight, okay, so what are you getting? The in situ stress. So which way looks like this. Okay, we can observe that in how that in the stress becomes that in the uniform. Yeah, so if we go into the first step, you can see first step which is stress there. Yeah, if we using this scale, yeah, almost everywhere is that 0. Yeah, so then that will quickly, yeah, which will becomes okay. You look at that in this process. Yeah, which actually we just run a few of the steps. You will see that. Yeah, you look at that again. Yeah, so quickly it goes in that into the stress and so. Yeah, so then finally you look at that everywhere. So that's 60. Okay, so this is the case without of that in the self weight. Actually, you can consider that with the self weight. Okay, if you consider that in the self weight, so then in that case you will have that in the gradients. So like into this one. Okay. Yeah, so what direction of that in the stress? Okay, so I need to change that in the scale. Okay, so this is that's in the. Okay, so let me check in this one. Yes, so this that's no gravity. So let's look at that with gravity. No gravity. Yes, you can see with that in the gravity. So then you have that in the stress at the top and at the bottom. So it's not the same. Yeah, actually, so that's the difference is here. Is just this one. Then add the self weight caused by this rock masses. So then you will get this one. Okay, that's the first step of the calculation. Okay, the first step calculation, what we wanted is that after the first step of the calculation, which will generate me, yeah, of that's the file, which I needed this file. Okay, which will have that's the initial stress. Actually, I only need that's the loss of that in the file. Okay, let me come back into the PowerPoint presentation. I show you what is that. Okay, so this is that we calculated the initial of the stress. So after that initial stress, what I wanted to that, after that in the calculation, which we're getting a number of this kind of a file for each of the step of your output, which we have that in the input file. Output of the file, which will include in the initial of the stress, actually, which is included in the code. So we only need to what is the last step when you have already achieved the static equilibrium. Okay, so here, yeah, I calculated that the 300 thousandths for the expression of the integration. That's not a big step. Yeah, so for my computer, just need a few of the millions. Yeah, actually, so is that you just need to have a break. Yeah, so we go to toilet, come back, then you will be have this will finish. Okay, so after I getting this one, I need to copy this one. Then I changed this file. Actually, which is I changed this that in the step. Yeah, so you can see here, this is that in, which is show that in the step, and then you change this one becomes final. Okay, so then after that, if you open this one, this file actually which includes this information is how many of that node, and what is that after we apply that initial stress, what is the new coordinate? So this is that the information which we need. Okay, so after we have that this information, then we copy this in the input file with that in the order of that in the two of that in the input file. Okay, so then order of that in the two input file. Okay, so let me for the step 2 of the calculation. Okay, step 1 we calculated it. Then for the step 2 calculation, we needed to 3 of the input file. Okay, one of that in this input file, as I said, this input file. So this is that what you getting from the step 1 of the calculation. And then the order of the two input file is the same as that in the step 1 of the calculation. But here we need to do some of the slightly of the changing. Okay, where is that in the slightly changing? Yeah, so now you should be quite familiar with the format of this, the input file. Okay, we have say this is that in the input file. This is that's the same as the previous one. Okay, so I have already go through that in the many of the times. I just show you that in the PowerPoint presentation. Okay, so let me go to that in the PowerPoint presentation. Let me swap my screen. Okay, we say for that input file, we already introduced many times before. Yeah, so that's the same. What do we have that's in the, what is that in the maximum number of that in the element? So maximum number of that in the node. Okay, then the parts. So the maximum number of the element in this part, maximum number in this, maximum number of the nodes in this part. For our case, what do we consider here? We only consider that in have one part. Sorry, one part. Yeah, one part, then in that case, you have this number actually, so that's the same. So we say in each of the part, we need to have that in the element connectivity and know the coordinate. So then after that, we have that in the initial of the velocity, so that's 0. Okay, so besides that, for the step 2 of the calculation, so we need to add an additional one, which is the coordinate from the initial stress analysis. So actually, so what we get in this is that from the previous of that in the input file, we say from the step 1 calculation. So what we from the step 1 calculation? Okay, sorry, I needed to go back. From step 1 calculation, we get into this one. Okay, so what you do actually, so we copy this data starting from here. Okay, we copy this data. That's the new coordinate. So after the initial of the stress calculation, we paste in that into that input file. Okay, pasting that to here. Okay, so then that input, then that file, we can drop in that file. We do not need that one anymore. Okay, so this is that to get the new coordinate after we apply that in the initial stress. Okay, besides that, so you notice that for the tunnel in the first step, so we have that in the rock mass is like this. So we have that in the tunnel here. Okay, the tunnel, in the second step, we need to have that excavated. In the first step, in order to get in the uniform of the initial stress, we actually keeping that in the rock masses inside of that tunnel here. But for the second step, we will excavated this part. Okay, for the excavated that in the input file, you need to tell that in the where you wanted it to excavate it. Okay, so that's what we have that in here. So we need to have an additional of that in the section. So which is called the excavation and the support. Okay. What we have here, we just needed to excavate it. We only have one set. One, that means we only needed to excavate one set. Okay. So then excavation. Okay, we using that in keyword excavation generation. That means you have here, so which is continuous. Okay, so I have this and that's in the element inside of this excavation, actually, which is the element number from 1 till that's in 6, 6 to 6. Okay, I say the element inside of this set which we excavated. How did I get in this? I using that from the opcode. Yeah, so this actually is the same as the opcode. In opcode, if you need to excavate something, so you define an element set as well. Then after that, so you remove that one. Okay, so here this is the same. I define that the element is set. So then I excavated that. Okay, so here you notice that I excavated that in the first step, excavated that. And I excavated everything. Yeah, obviously, if I wanted to install any of the supports there, I wanted to be able to do like this. But for my case, I have this unsupported tunnel. So I excavated one step or excavated many of the steps, it does not matter. But if you wanted to put in that in the support in there, so you needed to gradually soften. Yeah, so that's what is usually when you put in that in the using the two-dimensional method to put in that in the tunnel excavation. So we know that in the tunnel excavation, essentially, so this is a three-dimensional problem. Okay, if I draw that, okay, actual case, you have that in a three-dimensional, the tunnel is a three-dimensional problem. Okay, suppose we have that tunnel which is excavated in this side. So what we do, so we firstly excavated in this, then we will install the supporting system. Okay, I using that in the blue of the color, which is represented install that in the supporting system. And here, this is that in the supporting system. And then you have that in the tunnel excavation phase. Okay, I suppose I have here, this is that in tunnel excavation phase. And here, this is that rock you have not excavated. So what we do, we raise this tunnel, which is excavated. When we excavated the tunnel, when you have that, they push it forward. So then you install the supporting system. So that means between your excavation surface, you always have an error. You have that's unsupported. Okay, for our case, we have this part. So this is not supported. This is not supported. So when I have that in the tunnel excavation going forward, suppose I have that in the surface, which is here, then in that case, I install the supporting system here. Okay, then that's where apply that in the load. So this is that's a usual case for you to use in the three-dimensional of that in software. But what you have here, we put in that using two-dimensional method. So two-dimensional method, if you put in that in the supporting system, you cannot one step of that excavation. You need to using the core softening. So the core softening, So why is that? Since if you install the supporting system completely excavation, then you install the supporting system there. So your supporting system won't carry any of the load, since in 2-dimension you do not have any of the disturbance. But for you, if you do not install the supporting system, it does not matter. I can excavate it one step. And I have that one step excavation, since I have this a dynamic relaxation of the process. And although I excavated one step, but actually I needed to calculate many of the steps to achieve that the static equilibrium. Okay, so this is a dynamic of the process. So that's actually what is in the reality. That's in the rockburst of the process. Okay, anyway, so here I have that's the excavated that's in the one step. Okay, then here, then remaining is that's given that's in the boundary condition, material property. Okay, so for this part, so as I introduced that before, so we using that in a software, a pre-processor. Okay, so let me show you that. Okay, so let me stop and to share my computer screen. Then show you that's in the input file. Okay, so then let's look at that in the input file. Yeah, so here I already introduced that in the compounded presentation. Yeah, so we starting from the parts. Okay, so then that's the element, the node. Yeah, so then the velocity. Okay, so I specifically introduced this. This is that's in the result we from the first step of the calculation, which is the new coordinate of each of the nodes. Yeah, then after that, we do that in the excavation. And this one means how many groups excavation. This one means, so that's which step I excavated that. Okay, so then this one, which means that what is that in the set? Okay, this is the same as that in the abacus. So in the abacus, if you have that the generate, that means you only need to have that in the first element and the last element, then the step of the size. So then, yeah, so the program which will automatically to find that of that the element inside of this set. Otherwise, if you do not have this one, you need to list all of that the element here. Okay, so that's the order of that in the way. Okay, so besides that, we have this that in the element property, and then is that in the node property, then the boundary node of the property. And for that, we say for this one, we were using that in the script. Okay, let me open that in the Visual Studio. Yeah, I say here we have a very simple of that in C++ program. Okay, so what I have that I already made into this one. Yeah, yeah, you can see here, this is that all of that in the presentation, which I introduced previously. And for this C++ script, I already, yeah, so put in that in synthesis computer, all of the previous one, which is available here. So what I do for this time, yeah, actually, so which is I just copy this one, then I slightly to change that. Yeah, so I already made that change, and this one I call that in the rockburst 2D of that in the file. Okay, after the presentation today, I will share this in C++ script to you as well. So you will notice that each time I just do the slightly of the change. Okay, let's open this one to see this one. Yeah, so what I do is that here, yeah, we go into the firstly. Okay, so what I do, which is related to this input in the file. Okay, so I given that in the slightly to change it. So previously for this problem, okay, let me change it. That's the red color. For this problem, we have the maximum, that's the number of the elements, so which is this one. Then the maximum number of the node, which is this one. Okay, I replace this. So then below that, Firstly, given that since we already have one of the material property is the rock, so I given that since everywhere, so I given that equal to 0. Yeah, so that's all. Since we already have one of the material, then for the node of the property, so I needed to given that ball. Okay, so initially I given that the everywhere I given that in 3. Okay, which is corresponding that's in here. Yeah, so which way corresponding into here? Okay, we have here 10 of the column. So we say this is that's in the first column, then that's the sorry, so that's the let's starting from 0. So this is column 0, then this one is column 1, column 2, column 3, column 4, column 5, column 6, and so on. Okay, so we say the first column we 0, so that's for the represented, this is the rock of that material property. And then the second, the column 1 and the column 2, I do not need to use that. Okay, for me, for the convenience, yeah, each time I do the it's okay, you leave that in there, although you do not use them. Okay, then for the third column, I use that to represent the rock of the property. Okay, so here that's the internal of that, and I do not need to given the boundary condition. Okay, then the remaining is that I needed to given that the boundary condition. Okay, so then what I label that into here. So for the left boundary, so I label that as 4. And for the right boundary, for the bottom boundary, yeah, I label that as 5. And then for the right boundary, I label that as 6. So then for the top boundary, I label that as 7. And then for one of that in the center point, I label that as 8. Okay, so how do you know that's a left boundary? Is that we define that in the sets according to, okay, so we define that in the set. Let me show you. So, okay, so let me clean my computer screen. Yeah, so in the of course we define this set. Yeah, I introduced that since before. Yeah, so of course it's very convenient to define the set, and each row you have that 16 of that number. Okay, let's look at that in the first one. In the course, I define that in the left boundary. Okay, this is the node of the node. Okay, what I use in this script, which is read this. Yeah, you can see this follow this. Firstly, so reading this keyword. Yeah, I'm reading this keyword. Yeah, so which is correspond to this one. And then this one, I'm reading this, how many of that number. I have 121 of the number. Then I make a loop, which is from 0 to 121. Okay, then I read the node number. Okay, so then I read that in the node number. Yeah, so since I have this is the structure of the data, each of that's 16 of that. And you can see if I have that inside of this row, so I have that format which is like this. If I have that at the end of this row, okay, at the end of this row, yeah, so let me clean. Yeah, at the end of this row, so you see that's in the, you do not have that the comments there, that's the difference. If you use the same way to reading that, then they which were reporting that's the error. Okay, then I reading this one. Yeah, then after that, this is just a circle, a loop to reading that. Yeah, but since I have that in the node coordinate, which is starting with 0, so then -1. Okay, so then I reading that in the node no. Then so previously I have this equal making that equal to 0. Then I overwriting this, so making that equal to 4. Okay, so then that will becomes 4, and so on. Okay, so each time you only need to slightly to change this one. Okay, if the remaining, I will not introduce into that. I will share you that in the info file. Okay, so then you run this one. The following space in text, I have not found it. Okay, so then I run this one. Yeah, I run this, which we are reading. That's in the input file. Okay, I can show you that's in the, if we give you that's the example. Okay, we reading this. Okay, so then I'm making this one as well. Okay, so the first one, reading that should be left boundary, you can see. Okay, let's go one step. Yeah, you can see here, what's the reach, that's the left boundary. And then the next one, which we're reading that 121. So if I continue, so the next one, which we're reading that in the first year of the node coordinate. Okay, then so on. In this way, left boundary, right boundary, bottom boundary, and there is a top boundary. Okay, so reading that. So after you reading that, you will get the output. Okay, so this is that's in the output. Okay, the output, which is this, okay, you just need to copy this one. So then you paste it into that in the input file. So this is what is that in the input file. Okay, so then here we needed to give that in the different boundary condition. Okay, let's come back into the PowerPoint presentation. So this is that in how I given that in the boundary condition. Okay, so through that one, we introduced how we get in this specify this boundary condition. Okay, I specified the boundary condition, which is like this. Okay, so for the majority of the part of the rock, I label that as 3. Yeah, I do not need to give any of the boundary, or you can give a self weight that's there. Okay, left boundary, I label that as 4. Then right boundary, I label that 6. Bottom boundary, label that 5. That's label that as 7. Okay, each of that, which is corresponding to one of the row. Okay, so this is that way I given that boundary condition. Okay, so 0 is this is not boundary condition, that's material property. We ignore that one. We starting from 3. Okay, 3, you can see what I given that boundary conditions here. So I actually, so what I given that here, the first step I given that 2, 2, 2, that means we given that in the safe weight. Okay, so I introduced that before. You can give the boundary condition. You can give this 0, 1, 2, 3, 4. Yeah, actually, so you can give. Okay, so 0, which means that's free. So you do not need to. If you have that 1, so that means we giving you a false. Okay, so that's 2 means we giving you an acceleration. So here actually we given that a safe weight, which means other of that in horizontal direction, vertical direction, we have that in the safe weight. Actually, for our case, we only have the vertical direction, we have that in safe weight. Then later in that file, you will notice we vertical direction, we given that in G equal to 9.8. Then and the horizontal direction, we given that equal to 0. So then that's although you given a safe weight here, so actually it does not matter. Okay, so then 4, looking at that, and so 4, we have that in the left boundary. Yeah, in the first step, yeah, what we given here, that's free as well. Okay, so 5, that's the bottom boundary. We fix that in the vertical direction. You can see where that's 3, I didn't introduce into that. 3, actually, you given that a velocity, but you given a 0 velocity actually means you fix that in the boundary. Yeah, so then 7, 8, 8, so that's this point. So you can see I put in that in 3 and 3. So that means I fix that in all of that in the direction. This is that in the first step. Then the second step, yeah, so I can retain of that in this boundary, or I can fix this boundary. Yeah, I fix that in the using the roller boundary, fix that in the vertical direction. And here I fix that in the horizontal direction. I using that retain of that in the initial of the stress. Okay, so this is that in the boundary condition. So after you given that in the boundary condition, then that's O. So then you can do that in the calculation. Okay, so then what do we get in that? Then the second step of the calculation, we have that in the input file. That's here. Okay, the second step of that in the. Okay, so you only needed to use this input file. The reason I put in this input file is that you have one of the section you needed to copy this data to there. Okay, another thing is that I needed to mention that for the second step of the calculation is that in here, when we do that in the first step of the calculation, yeah, I put in that in the 0. Then the second step of the calculation, I say this is that's in the simulate. So then I needed to give that equal to 1. Okay, so then the remaining you do not need to change it. That's in the running control of that in the file. Okay, so then after that, so you will run that. Okay, run that, and so you are getting the results, and which is like here. Okay, so after that you run that. I have this a few of that in the screenshot. So this is that in the initial of the step. Initial step you can see here. This is that you only had that in the stress concentration. You do not have any of that in the failure. Yeah, whether you have that in the calculation. So then that's where I have that in the fail. Okay. Let me show you that in the results in the parallel view. Okay, I already calculated this result, so let me get rid of this one. Okay, so after the calculation, yeah, I needed to demonstrate that. Okay, after that, you copy this 2 file. Okay, we copy this 2 file. Okay, 2, that's in the exe file. Okay, I have that in the exe file. That's here. Then I copied that. Okay, then you just need to run that. So then you are getting the results. Okay, here, this is that in, yeah, I calculated that in the rockburst. That's in step 2. Okay, then after that, I visualize the results. Okay, so I goes into D. So the rockburst is step 2. Rockburst in step 2 of the calculation. Okay, here. Yeah, I have that left A, which will show that's in the stress. Okay, let me show that in the joints as well. And for the right hand side, I will show that in the joints. Okay, so here I will show whether that's in the damage or not. And for this one, I show that's in the vertical of the stress. Yeah, so initially, so this is that you can see this is everywhere. So that's the stress is uniform. So that's why you do not show any of the stresses there. Okay, so then let's do the calculation. Let's do the animation. So you will see that's in the whole this. Yeah, after that's excavation, after that's excavated, which we're introducing that in the stress concentration, then the stress concentration, which is where causing that in the fail here. Since we have the vertical stress, which is bigger than the horizontal stress, which is causing the stress concentration. And this stress concentration with the fail around the tunnel, which will further propagate to into the tunnel, and you will have the stress concentration, which further goes into the deeper of the tunnel, which will continuously propagate. So then which will have the fail. Okay, so that's which we're getting the results from my PhD student. They published in that paper. Yeah, so obviously in that paper, which is more comprehensive, which did a parametric analysis. Yeah, so I will leave that to you. For this one, you can change it. Yeah, we say we apply that vertical stress, which is 60 megapascal, horizontal stress, which is 45 megapascal. You can change it that one to change that's the lateral suppression coefficient K. You can also add an one of that's in the Johnsons here. Yeah, so that's in the Johnson. You can be that's a field of the Johnson, or that's in the opening of the Johnson. You can change it. That's in the geometry of this in the tunnel as well. Yeah, so here what I using here, that's the circle of that in the tunnel. So you can change it. That's in the square of tunnel, or that's in the whole shore of that in the tunnel. Yeah, okay, so that's the many of the this calculated many of the staples. So actually I calculated the 5 meaning of the staples. Yeah, so that's why you have that last one, which is 500 as starting from 0. That's why you see that's 499. Okay, this is that's they calculated the final of the results. So you can see for these cases, we have that you have that the failure, which is only around that's in the tunnel. You have the majority of the part, so you do not have that failure there. So we actually, no matter you have that failure or not, we always insert in that in the cohesive element. Yeah, actually here we wasted a lot of the computation of the uh, capacity. So for this error, since you do not have that failure there, it's unnecessary for you to insert of the cohesive element. So that's in the FDEM, they have 2 methods to insert the cohesive element. One of that, which is what I showed that here, which is called the eccentric cohesive zone model. So RCZM. For these cases, no matter when you have that failure occur or not, I always insert of the cohesive element. There is another of the method which is called the extrinsic cohesive zone model. So this is that for the where if you do not need a failure, so then we do not insert of that in the cohesive element. Yeah, I mean that's a failure means that's in the damage. Yeah, so instead of that in the failure. If you do not have any of that in the damage there, you do not need. Okay, so damage, yeah, I mean that's in this value. Okay, so let me order adjust this one. Let me order adjust this value. Okay, I have this. So we say that's the damage is from 0 to 1, only when that's equal to 1. Yeah, so actually, so what you see that's in the cracking when d equal to 1, so then that's the crack, which is smaller than this one. Yeah, we have that ECZM actually is available in our software as well. Okay, so let me clean this one. I show you that's none of that in the model, which is the same of this model. I use that in the extrinsic of that in the model. Okay, I have another one, so that's here. I show that in the stress. Yeah, then here I show that in the joint. Yeah, okay, so, sorry, let me. Okay, so the rockburst ECZM. Okay, so this one I show that. Then this one I will show that in the joint. Okay, then we show that in the damage. Mm-hmm. Not this one. Yes, bear with me for a while. So let me find the that's in the ECZM model. So rockburst, rockburst. Okay. Yes. So let me bear with me. Let me find the that's in the model. Yeah, I have that here. Yeah, sorry. Okay, so let me find that one. Yeah, okay, so let me show this, that's in the damage. Yeah, so then this shows that's in stress. Okay, you look at that in the difference compared with previous video. Okay, let me show that. Yeah, you can see here. Yeah, only the case when I have that in the damage, the potential of that in the damage occur, then in that case, yeah, I insert in the cohesive element here. Unlike for the previous case, I insert in the cohesive element everywhere. So that's so-called that's in the extrinsic cohesive zone model. So if you reading that in the paper about the cohesive zone, so they have two models. One of that which is called the RCZM, and then the other one which is called the ECZM. So ECZM, which is much more computational of that efficient. So that means in this error, if I do not insert enough that in the cohesive element, this is there. So it's unnecessary for me to deal with the cohesive element there. So that we're saving so a lot for that. Yeah, you can compare that in the two cases. The two cases are almost getting that in the exactly the same of the results. Yeah, okay, so I stop here. Yeah, so I handed this back into Futian.